All right, so we'll move on. We've established our finite dimensional weak form. We've looked at our basis functions. We made the somewhat important observation that for this problem, because we have a vector problem, the number of nodes is not identical to the number of degrees of freedom, right? But then we made the identification and we know how to relate them. All right, let's go on. We'll get into assembling the integrals in our weak form, in our finite dimensional weak form. So we will call this segment the element integrals. And in order to get to the element integrals, we first need to make the observation that our finite dimensional weak form, because it is an integral over the entire domain, right, or the boundary or the relevant Neumann boundaries, also allows us under this partition to write it as a sum over the individual sub-elements, right, or the sub-element boundaries. Okay, so the finite dimensional weak form can also be written as sum over E, integral over omega E, W H I comma J, sigma H I comma J, dV equals sum over E, integral over omega E, W H I Fi dV plus. Now here we need to be a little more careful, right? We are talking here of doing the following. We are talking here of doing a sum I equals 1 to NSD. Okay, we're summing here over our spatial dimensions, and whereas earlier we could directly put down the corresponding Neumann boundary, we are going to write that also as a that integral also as a sum over subintegrals, right? Each of them is a boundary. So we need to say here that we are going to take this sum not over all the elements, but the elements belonging to let me see, right, E n, right? Remember, E was a set of elements that had one of their boundaries coincide with the Neumann boundary. All very well, except that that too needs to be indexed by the spatial dimension, right? Because for each of the i's, I equals 1, 2, 3, we could have a different set of elements whose boundaries coincide with the Neumann boundary for that particular dimension, right? Okay, so we have that, and then the integral is over partial omega t bar I, and I'll put the E up there, right? And this, of course, is the same, WHI T bar I D S, right? And all right, so this is what we have. What we're going to do is, just as before, assemble each of these integrals over the element subdomains, or in this case over this special element boundary subdomain, right? And of course we are also going to use the fact that this is given to us by the elasticity tensor, now multiplying U, K, comma L, right? Okay, so we are going to proceed with this now. So we will, as always, start with the left-hand side integrals. consider first integral over omega e wh I comma j. I'm going to directly go to the representation including the elasticity tensor. Okay, so sigma h ij. Oh, if I'm going to use a sigma h, I need to have an h there, right? Because that's where the finite dimensionality of this comes in. Okay, so we have here c I j k l u h k comma l dv. Right? Now on a previous slide belonging to the previous segment, we wrote out the expansions for WH and for the gradient of WH and for the gradient of UH. We will now invoke those, right? And in doing so, I'm going to write it here. We have here, again, allow me to skip, well, okay, I won't skip a step right away. I'm going to write this as an integral over omega e. The WH I comma j is written as sum over a NA comma j C A I E. Okay, this is WH I comma j, and I put it in parentheses. We have here C I J K L, and again we have sum over B NB. Now the gradient is represented as a using the coordinate direction L, right? Of course it's L runs over 1, 2, 3. So that means that NB here has to take a comma L, right? That's where the gradient is computed. And we have D, B, K, E, dV. Okay. Now, if you were to go back and stare at the way we did the corresponding step for our scalar 3D problems, you would see something very similar, except the fact that we had no index on the degree of freedom, the degrees of freedom for the weighting function, nor on the degrees of freedom for the trial solution, for the displacement field. Okay. The fact that we do have indices here comes from the fact that these are, after all, vector degrees of freedom, and I and k here both run over 1, 2, 3. And the fact that we have those indices also shows up in the fact that we have a couple of extra indices here, right? The coefficient there, if you want to think about it as that, the elasticity tensor is, after all, a coefficient of elasticity, is a fourth order tensor, unlike the conductivity tensor or the diffusivity tensor, which are second order indices, right? So that's really all there is. And once we understand that and we are comfortable with that bookkeeping, essentially, all is well. Right, so we'll proceed, and as you may imagine, what is the next step here? Or as you may recall, what is the next step? Right, it is to observe that the degrees of freedom, never mind the fact that they're vectors now, are still, after all, independent of position, right? And so they can be pulled out of our integral, and in doing so we can also, because integration and summation in this case commute because of linearity and all that, we can pull those summations also outside the integral, right? Okay. What that gives us is, now I'm going to write this as a sum over A and B. And let's remember just here that A and B run over 1 to number of nodes in the element, right? Integral, oh, sorry, okay, I need to have here C, A, I, E. Okay, I have here NA comma J, okay, C I J K L, right? And for our representation of the gradient of the displacement, from that representation of the gradient of the displacement, we get an NB comma L here, okay? dV, right? I put a parenthesis here, or a pair of parentheses, and right, what we've done in the process is pull the dB KE out. Okay, right? Straightforward enough. Oh, this is an integral over omega E, right? To proceed, and remember that we know how to compute these gradients, right? We looked at that on a at the end of the last segment, right? So we know how to compute these gradients, no problem. All right, let's move on. Remember what the next step is, right? It is to convert it to, we carry out a change of variables and rewrite the integral here as an integral over the bi-unit domain. So, once again, sum over A and B, and I'll forego writing the limits of that sum. We get here C A I E integral over omega C, right? That's our parent domain. NA comma J C I J K L NB comma L. Right, now just as before, dV can be written as determinant of the Jacobian of the mapping dV sub, I think I was putting it there, right? Okay. Now, of course, I could rewrite this in another step by specifying that this integral over omega c really involves integrals of C1, C2, and C3. It's a triple integral, each of them going between -1 and 1. And the fact that this is essentially dxc1, dxc2, dxc3, right? And this integral basically becomes something like, it becomes actually a triple integral, right? -1 to 1, -1 to 1, -1 to 1, right? So that step is given, right? So well, we can go ahead and compute it. Now observe that in general, depending upon the basis functions we've chosen, whether we decided to stick with trilinears or triquadratics or went higher order, these are functions of C1, C2, C3. Now the way I've constructed this, I've been thinking to myself at least that C is independent of position. Doesn't need to be, right? In general, it too can be a function of position, right? That would allow us to go to inhomogeneous materials. Okay, all of that would simply add a higher order dependence on position to this integrand. And of course, we know that in general, the determinant would also involve a dependence upon position. Okay, but nevertheless, we not integrate this, right? We do numerical quadrature, right? So we do numerical quadrature or numerical integration, which is quadrature. Right, and since we are working here with Lagrange polynomials defined on hexahedral elements, we have available to us the optimality of Gaussian quadrature. I ought to admit here, though, that if our elasticity tensor has some strange dependence upon position that is not just polynomial, the Gaussian quadrature may not remain optimal. right? But still, it's an approximation, and that approximation is understood. Okay, so essentially we know how to compute this, right? Let's assume that we go ahead and compute this, right? If we go ahead and compute it, let's write it out. Okay, let's write it out, and let us write it out in this fashion. Okay, so right, so this thing is now equal to sum over A and B, C A I E. We've carried out the integral. Okay, so we have something in there. So this entire integral here that we have here, this whole entire integral is done. And I realize now that I omitted to write my dB KE here. Okay, that integral with the brace bracket is done. So when that integral is done, we will be left here with a dB KE, which is this one, right? Okay, I've left an amount of blank space there because I want to fill it in with something. And I want you to think of what kind of object goes in there. In particular, is it a scalar, a vector, or a tensor? As a guide to getting to that answer, recall that the integral that we're trying to work with here is the one that I am now showing to you on this slide, right? It's the one that is written next to the word consider. What kind of an object is that? Is that integral itself, once you evaluate it, is that a scalar, vector, or tensor? Right? It is a scalar, because though the C has free indices I, J, K, L, those are all being contracted out, right? And a sum over each of those dummy indices, I, J, K, L, is indeed implied. Okay? So what we expect to see is that this thing is a scalar. But the way we've constructed it, we see that the CA, the C and the D, right? By C here I mean this C, not the elasticity tensor. The degrees of freedom have indices, free indices. If the final thing is to be a scalar, there have to be other free indices, and whatever object is going to go into the blank space, which will be contracted out with I and K. Okay? So whatever object we have here, I'm going to denote it as K. Of course, it will also have free indices I, K. Okay? Right? And it is essentially that integral. Okay? So the integral that we have here is Ki, K. Okay? It is a particular component, the Ik component of a tensor. Right? Thought of as a matrix, it is a 3 by 3 matrix, right? Because I and K run over 1, 2, and 3 because we're operating in 3 dimensions here, right? Now there's something else I haven't added there, and can you tell me what can you think of what it is? The indices A and B, right? Because those indices are still here. So anything that we compute for the integral is specific to the combination of nodes A and B which went into that integral, right? That form that integrand. So we have an object here which I'm going to write as KAB IK. All right? Now there are indices all over the place here, and it's useful to think to just sort this out. So when I say I comma K go over 1, 2, 3, I'm going to write here the the statement that's almost a contradiction in terms, which is that a sum is implied. Okay, over ik. So I do not have an explicit summation here. But over the A and B indices, I do have an explicit summation. Right? It's just a matter of taste in terms of what I choose to write as an explicit summation and which I choose to invoke the Einstein's summation convention on. Okay? The fact that I'm invoking Einstein's summation convention on the spatial indices, spatial dimensions, comes from a sort of hangover of continuum physics.